So the next one is waves, wave fronts, and rays. We often use the concept of a wave front to describe wave propagation. We define a wave front as the locus of all adjacent points at which the phase of vibration of a physical quantity associated with the wave is the same. That is, at any instant, all points on a wave fronts are the same part of the cycle of their vibration. So what is this wave fronts talaga? For example, is when we drop a pebble into a calm pool, the expanding circles formed by the wave crest as well as the circles formed by the wave troughs between them are called wave fronts. Example niyan is ito. Nakikita niyo yung bilog-bilog na yan na wave. It will be look like this. Meron siyang crest and may troughs. And ang tawag dyan sa nakaumbok na yan is the wave fronts. Yan siya, the wave fronts and the wave crest. Yung dito na area, wave fronts, wave crest, and so on. Similarly, when sound waves spread out in still air from a point-like source, or when an electromagnetic radiation spreads out from a point-like emitter, any spherical surface that is concentric with the source is a wave front. For example, in this figure, the diagram of wave motion, we usually draw only parts of a few wave fronts, often choosing consecutive wave fronts that have the same phase and thus are one wavelength apart, such as crest of water waves. While one wavelength apart, tulad dito, they are one wavelength apart. Similarly, a diagram for sound waves might show only the pressure crest, the surfaces over which the pressure is maximum, and a diagram for electromagnetic waves might show only the crest on which the electric or magnetic field is maximum. To describe the direction in which light propagates, it's often convenient to represent a light wave by rays rather than by wave fronts. Rays were used to describe light long before its wave nature was firmly established. In the particle theory of light, rays are the paths of the particles. From the wave viewpoint, a ray is an imaginary line along the direction of travel of the wave. In Figure 3.5a, the rays are the radii of the spherical wave fronts. Radii, big sabihin, kalahati ng diameter is radii. So, kinoconsider na ang rays is just the length of the radius of the circle. Kasi, ang sabi nga dito is, wave will travel from a point source, just like in this sphere, from this point source, and the rays are away from the point source. That is forming a spherical, parang spherical aura, ganun. And then, the rays are from the point source up to the end of the ray, and that is a radii. Okay? Next. In Figure 3.5b, they are straight lines perpendicular to the wave fronts. Okay? Like in this one, this is a straight line perpendicular to the wave fronts. When waves travel in homogeneous isotropic material, a material with the same properties in all regions and in all directions, the rays are always straight lines normal to the wave fronts. Rays are always straight lines normal to the wave fronts. Okay, when we say normal, it's halimbawa ito yung wave fronts natin, since this is Ano nga tawag dito? Nakahiga. Ang normal niya is pataas. Okay? Pa ganon. Pa ganon. Ang sabi dito is, the rays are always straight lines normal to the wave fronts. Okay? At a boundary surface between two materials such as the surface of a glass plate in air, the wave speed and the direction of a ray may change, but the ray segments in the air and in the glass are straight lines. The next several chapters will give you many opportunities to see the interplay of the ray, wave, and particle description of light. The branch of optics for which the ray description is adequate is called geometric optics, and the branch dealing specifically with wave behavior is called physical optics. Next, 3.2 reflection and refraction. In this section, we'll use the ray model of light to explore two of the most important aspects of light propagation, the reflection and refraction. When a light wave strikes a smooth interface separating two transparent materials such as air and glass or water and glass, the wave is generally partly reflected and partly refracted into the second material, as shown in this figure 3.6a. Okay? For example, when you look into a restaurant window from the street, you see a reflection of the street scene, but a person inside the restaurant can look out through the window at the same scene as light reaches him by refraction. So, from this coffee shop, sila angkol, nakikita nila yung reflection sa labas by this side of view. And si babae naman, ang nakikita niya is yung reflection sa labas dahil nare-reflect yung light from this labas into her eyesight. Okay? This is a form of reflection, and sila angkol sa loob, ang nakikita nila is a refraction. It means that the light is emitted from this area into their eyes. So, ang nakikita nila is si labas. Ang labas lang ng kabilang window. Refraction ang tawag doon. Sana tayo. We describe the directions of incident, reflected, and refracted, which means transmitted rays of a smooth interface between two optical materials in terms of the angles they make with the normal or the perpendicular to the surface at the point of incidence, as shown in figure 3.6c. 3.6c, the representation simplified to show just one set of rays. So there's an incident ray. Incident ray is yung pinagmulan ng light. For example, an image. Nireflect niya into here. So nagkaroon ng angle of reflection, and also hindi lang niya nireflect kundi nirefract niya. Meaning to say, yun yung nangyayari sa loob dito kila angkol. From incident ray, na-refract siya into their eyes. So, ang napoperceive nilang picture is yung outside. While itong si girl sa labas, ang napoperceive niyang picture is yung reflected ray, which is also yung image sa labas. For example, itong hat niya, nakikita ni girl yung kanyang hat na lumipad. Next, if the interface is rough, both the transmitted light and the reflected light are scattered in various directions, and there is no single angle of transmission or reflection. Reflection at a definite angle from a very smooth surface is called specular reflection, from the Latin word mirror, or then the scattered reflection from a rough surface is called diffuse reflection. This distinction is shown in figure 3.7. Both kinds of reflection can occur with other transparent materials or opaque materials that do not transmit light. The vast majority of objects in your environment, including plants and other people and this book, are visible to you because they reflect light in a diffuse manner from their surfaces. Okay, ano nga yung diffuse manner? Rough surfaces. Our primary concern, however, will be specular reflection from a very smooth surface such as highly polished glass or material. Unless stated otherwise, when referring to reflection, we will always mean specular reflection. Ano nga again yung specular reflection? Ito yung in a very smooth surface. Figure 3.7, specular reflection and diffuse reflection. Yung pagkakaiba nila, since hindi patag or rough siya, some of the incident light will not be reflected uniformly. Merong nandito, merong nandun. Wherein sa specular reflection, all of the incident lights are reflected uniformly. The index of refraction of an optical material, also called the refractive index, denoted by N, plays a central role in geometric optics. It is the ratio of the speed of light, c, in vacuum to the speed in the material, and we get equation for index of refraction 3.1. N is equals to speed of light over the V. Light always travels more slowly in material than in vacuum. Of course, sa vacuum air lang yung nagta-travel si incident light through air, wherein material nagta-travel si incident light through either specular reflection or smooth surfaces or rough surfaces. So the value of So the value N in anything other than vacuum is always greater than unity. Always greater than 1. For vacuum, N is 1. Since we are considering only air in a vacuum. So the index of refraction is always 1. And since N is a ratio of two speeds, speed of air over speed of light, it is a pure number without units.